about this particular curve. And the first question A says, find or determine the values of A and B which define the domain of the graph. The values of A and B which define the domain of the graph. So the domain of the graph refers to what are the extreme position values of x. What are the extreme position x coordinates? Now the extreme position would be here and here in terms of the x values. The graph or the curve doesn't go further to the left than this point or further to the right other than that point. So those are the extreme positions. So the domain would be the x values that define those extreme positions, the x coordinates of those points. So if we come down onto the x-axis, this would be one extreme value. And if we come down on the right-hand side, this would be the other extreme value. So therefore, this would be one value in the domain. This would be the A value. And this one here will be the B value of the x coordinates. So your answer to that will be A should be equal to -2 and B should be equal to 4. Right? A will be equal to -2. A will be equal to -2 and B will be equal to 4. Okay, so that will be your first answer. Values of A and B which define the domain of the graph. A would be -2 and B would be 4. Part B. Part B said determine the values of x for which x squared minus 2x minus 3 is equal to 0. In other words, find the values of x for which this function x squared minus 2x minus 3 is equal to 0. Now we learned that when we put the function equal to 0, in terms of a graphical representation, that will be where the graph cuts the x-axis. Right? If you check back your notes, that is what it is. When we did the notes in the last class, we said that if we take the function, put it equal to 0 and solve that particular function, then the answers that we get would tell us where the graph cuts the x-axis. If you check back your notes, you'll see that. So therefore, if in part B they're asking us to determine the values of x for which x squared minus 2x minus 3 equal to 0, we would have to look at the points where the graph cuts the x-axis. That would be one point there. And this would be another point right here. Those 2 points there would be where it cuts the x-axis. So the answer for that would be either x is equal to -1, like here, x equal to -1, good, or x equal to 3, x equal to 3. Okay, those would be the 2 points that would define the positions on the curve where x squared minus 2x minus 3 equal to 0. In other words, where is it that y, right, which is the same thing as f of x, is equal to 0? Where is it on this curve that y is equal to 0? And we know that y equal to 0, right, is on the x-axis. Wherever the curve intersects the x-axis, that is where y will be equal to 0. And that is why we know it will be at those 2 positions as well. So far, we have answer to A was A equal to -2, B equal to 4. The answer for B was either x equal to -1 or x equal to 3. Right? Those are the answers we have so far. Part C now. Determine the coordinates of the minimum point on the graph. Determine the coordinates of the minimum point on the graph. Now the minimum point on the graph will be the lowest point on the graph, the bottommost position. So the minimum point will be right here. That's where the graph bottoms out. That minimum point, if we look at it carefully, will have coordinates x value of 1, right, this is this one here, a y value of minus 4, which is this minus 4 here. So the coordinates of that point will be x equal to 1, y equal to minus 4. So your answer for C is 1 minus 4. Okay, so that will be for C. For D, determine the whole number values of x for which x squared minus 2x minus 3 is less than 1. What they are asking us to find out is where this function is less than 1. Where is x squared minus 2x minus 3 less than 1? That's what they're asking us to determine. Okay? Anytime you're faced with this type of question, the first thing you'll do is to find out where it is equal to 1. And then you could work out the other parts. So we are looking first of all at where x squared minus 2x minus 3 is equal to 1. That's the first thing we'll look at. Now x squared minus 2x minus 3 is the curve that we see on the screen here, on the board. So where it will be equal to 1 will be 2 locations. And those 2 locations I will just highlight to you now. It will be equal to 1 along the line where y is equal to 1. Right? And those locations will be, one will be here, because this is the line y equal to 1, this line here, and one will be here. Okay? So there will be 2 positions where x squared minus 2x minus 3 will be equal to 1. That will be here on the curve, where that curve here there, that curve will be equal to 1 here, and it will also be equal to 1 here, because remember the curve is the same thing as the y value. So the y value is equal to 1 here, and is equal to 1 here. So the curve value is equal to 1 at those 2 positions. Now, the question then asks you where it was equal to 1. The question asks you where it was less than 1. So now, we have to determine where this curve is going to fall below this line. Because anytime the curve falls below the line, it is no longer equal to 1, it is less than 1. Because below this line means go less, right? So anytime the curve goes below here, it is less than 1. And that occurs for values in between this point here and this point here. Okay? Values in between those 2 points. So what we'd have to do is to recognize what are the whole number values between this point on the left and this point on the right. Now, the integer values between these 2 points, integer, let's talk about integer, will be minus 1, 0, 1, 2, and 3. Let me say it again. The integer values of x between these 2 extreme points that we just noted would be minus 1, 0, 1, 2, and 3. Those will be the x values in between there. However, they didn't ask us for integer values. They asked us for whole number values. Now, whole numbers are numbers that are counting numbers, but also include 0. So the numbers that we will be talking about would be 0, 1, would be these numbers here, 0, 1, 2, and 3. Those would be the whole number values they're talking about, right? That would be, that would satisfy the requirements. So the answer for D, the answer for part D, let's write that down here. The answer for part D would be the whole number values for x, for which x squared minus 2x minus 3 is less than 1, would be these values. X equal to 0, x equal to 1, x equal to 2, x equal to 3. Those are the whole number values, right? Because you're looking for the numbers in between these two extreme positions that we noted. We cannot include minus 1 because minus 1 is not a whole number, it's an integer. So we have to leave that out. We could only include these numbers here. So that's the answer for D. The answer for E now. The gradient. They want us to find in D, determine the gradient of f of x equal to x squared minus 2x minus 3 at x equal to 2. So it means they want us to find the gradient at this point here. Right? This point here is where they want us to find the gradient. It's right there. But to find the gradient of a curve at a point, what you have to know is that you need to find the gradient of the tangent at that point. The gradient of a curve at a point is the gradient of the tangent to the curve at that point. And they already gave us the tangent at the beginning of the question. So all we have to do is to find the gradient of that tangent. Now to find the gradient of a tangent is just like finding the gradient of any line. You would use the equation y2 minus y1 over x2 minus x1 to find the gradient of that tangent. So if we are going to use that, m, which is the gradient, is y2 minus y1 over x2 minus x1. If we are going to use that equation, we need to get 2 points on the line. Now the 2 points on the line that I selected, you could select any 2 points on that line and find the gradient, but the 2 points that I used were this point here and this one here. Okay? This point here has coordinates x equal to 4, y equal to 1. So the coordinates here is 4, 1. Another point on this tangent, I said, was this one down here, and that coordinates, the coordinates of that point would be 2 minus 3. 2 in the x direction, minus 3 in the y direction. Okay? 2 minus 3. So, based on that now, we could deduce what the gradient at that, of that tangent would be at that point. And we're going to use the one at the top, we'll use that as x1, y1. We'll call this one here x1, y1. And we'll call this one below here x2, y2. Okay? So now, when we are using the equation, we could put the relevant and the proper figures in there. So let's put the figures there. y2 minus y1 will be minus 3 minus 1. So I'll put that on top. Minus 3 minus 1. And x2 minus x1 will be 2 minus 4. 2 minus 4. So we write that down. 2 minus 4. So therefore, we get that m, which is the gradient we're interested in, will be minus 4 on top, because minus 3 minus 1 is minus 4, over minus 2 below, because 2 minus 4 is minus 2. Minus 4 divided by minus 2 is equal to positive 2. So what we just deduced there is that the gradient of the tangent at the point 2 minus 3, sorry, which is the gradient of the curve at that point, is 2. So the answer for E will be 2. The answer for E will be 2, where they ask you to find the gradient of f of x at x equal to 2. Gradient of f of x at x equal to 2, which was that point there. Okay? Again, that was taken from May, June 2006, question 5. What that means is that that question is a compulsory question. It's a question that you cannot get away from. If they bring it, you have to do it. Okay? And after going through this, you would realize that there are quite a few things involved there. Right? And it's not something that you may get in the first look. You might have to go it over a few times well. Alright? So go through it. Ask yourself whatever relevant questions. If you have anything, bring it back in another class and we'll deal with it. Okay? But it is important. This is an important question. Alright? This was actually a whole question, maybe worth 10 to 12 marks. Right? Okay. Okay, so the topic we'll be going on to now is as follows, so you could write it as I call it out. Volumes and surface areas is the topic. Volumes and surface areas of simple right solids. Volumes and surface areas of simple right solids. Okay, so the first one we'll speak about is a prism. So you could write it down. A prism is a uniform solid. A prism is a uniform solid that has the same shape, or cross section along its length. Along its length. Full stop. The volume of a prism, is equal to A multiplied by L. Volume of a prism, let's call that volume V, is equal to A multiplied by L, where A is the cross-sectional area, of the regular cross-section, and L is the length perpendicular to the cross section. Okay. Right below that you write the surface area of a prism is equal to the sum of the area, the surface area of a prism is equal to the sum of the area of all the faces. The surface area of a prism is equal to the sum of the area of all the faces. Okay, so the first thing I want to illustrate is what is a regular cross section. If I draw this shape here, right? That shape is a cone. It's a cone. And if we look straight onto this cone like this, in this direction, we will see a circle. Not so? See a circle. If we were to cut the cone along that line, remove the portion on the left and view it again in the same direction, we would see another circle. The first circle, let's say, when we view, will be like this. And if we cut it and view it again, the second circle will be like this. Okay? And the reason that there's a difference in the size of the two circles is because the cross section is not regular. The cross section changes as you move along the length of the solid. Okay? So this is an example of a solid that does not have a regular cross section. If, however, we were to consider this shape or this solid, okay, could have been drawn a little better, but if you consider a solid like this solid is what we call a cylinder, right? And if we look at the cylinder from left to right, we would see a circle, just like in the first case with the cone. The difference, however, is no matter where we cut it, if we cut it here, if we cut it further along the length, and we view in the same direction, we will always get the same exact circle, right? The same exact cross section. So we say that this shape, right, this particular shape has, or solid has a regular cross section. And that is what makes it a prism as compared to the first one, which is not a prism, it's actually a pyramid. And we'll talk more about pyramids when we go further along in the discussion. So let us look at some prisms and look to see how we would calculate the areas, the total surface areas and the volumes. So if I were to draw a prism like this, where all of the sides are the same length. So let's say this side here was S, this side here was S, and this side here was S, right? Side, side, side. All of them have the same dimension. Then if we wanted to find the volume of this particular shape, it would be, this shape would be a prism. And the reason we are saying it would be a prism is because it would have a regular cross section all the way through. So if I were to consider this face here, that face would be a square, right? Because it would have same dimension, S by S. And it would have that square cross section all the way through if we are going in this direction. It would have that same shape all the way through, same exact square. So this is a prism. Now the volume of a prism is given as A multiplied by L, where A represents the cross section, area of the cross section. So the area of this cross section will be S multiplied by S, and then you have to multiply that by the length that is perpendicular to it, which would be this length here, from here to here, which again is S. So that our volume in this case will be S by S by S, which is S cubed, right? So we learned that the area, that the volume of a cube is S cubed. Okay, so take that down. Right, the next prism that we will look at is a cuboid. Right, so we're looking at now a cuboid. So what we have on the board there is a cuboid. And if, for example, this cuboid had a surface to the front like this, which had dimensions b for breadth, d for depth, and then it had a length given by L, what we would say is that the volume of this cuboid V, which is given by the cross-sectional area times the length perpendicular to it, will be the area of the front face here, which would be B multiplied by D times the length that is perpendicular to it on top. That will be L. So the volume will simply be BDL. So the volume of the cuboid is BDL. Right? Breadth by depth by length. Okay, so take that. Okay, the next one we'll be looking at is a triangular prism. And in this triangular prism, what you would see is that one of the faces, the face to the front, is a triangle. So this face here is a triangle. So in order to find the volume, what we'd have to say is the volume would be the cross-sectional area multiplied by the length. The length being that length there at the top. So the volume in this case would be the area A of the triangle. So area of the triangle multiplied by L. And the area of that triangle could be found in various ways depending on the information given. We learned that there are three ways to find the area of any triangle, right? Three methods, and whichever one you use is dependent on the information that they give you. So you could always review that. Up to now, in order to find the surface areas of each one of those, what we would do is simply find the areas of each one of the faces and add them up together. Okay, if we had to find the surface areas of each one. The next thing we look at is the cylinder. Now a cylinder can be either positioned vertically or it could be placed horizontally, right, on its side. And if we had to find the volume of that cylinder, the volume again is the cross-sectional area of the uniform cross-section times the length perpendicular to it. In this case, in this particular prism, which is the cylinder, the area will be that of a circle. And the area of a circle is given by pi r squared. So we would put area as pi r squared, and then we would multiply that by the length perpendicular to that face, given by the length L or the symbol L. So it will be V is equal to pi r squared L. Okay, so we could write it down simply as pi r squared L would be the volume of the cylinder. Pi r squared L. The next thing we look at is the curved surface area and then the total surface area. So we're looking now at if we had to find the curved surface area and the total surface area of a cylinder. Now if we were to imagine this cylinder as shown on the left hand side and an imaginary point selected there where just to the left of the point is called A and just to the right of the point is called B, and we were to imagine taking the scissors and cutting right down until we reach the bottom, then opening that circle out so that it becomes a flat sheet like this on the right hand side. Then what you would appreciate is that the leftmost point here will be A and the rightmost point here will be B. Good? So it is clear to see that the circumference at the top here, once opened out, will become the length at the top, which will be the length of the rectangle on the right hand side. So the curved surface area of this cylinder would be opened out to be the flat surface area of that rectangle if we were to open it out in that manner. And we know that the flat surface area of the equivalent rectangle to this cylinder's curved surface area would be found by using the length at the top, which is the distance from A to B, by the breadth or the height here, which is L. Now, the length at the top is equivalent to the circumference of the original cylinder. And the circumference of any circle is given by 2 pi r. So that's how we get the distance AB to be 2 pi r, because that's equivalent to the circumference of this circle at the top here of the original cylinder. So the area will be the length at the top, which will be 2 pi r, multiplied by the length perpendicular, which is represented by L. So the area of that shape, that rectangle, will be 2 pi r L. 2 pi r L, which will be equivalent to the curved surface area of the cylinder. So we could write that the curved surface area would be equal to 2 pi r L. Curved surface area, 2 pi r L. And the total surface area would be dependent on if the cylinder is, first of all, open at both ends, then the total surface area will be the same as the curved surface area. If it is closed at one end, then we'll have to include the area of one of the circles. Let's say it was closed at the bottom, right? Like a waste paper basket, closed at the bottom. So when you throw the stuff in at the top, it wouldn't fall out the bottom. So we'd have to include in addition to the curved surface area, 2 pi r L. If it was closed at one end, we'd have to include one circle, which would be pi r squared, right? Because the area of a circle is pi r squared. But if it was closed at both ends, let's say a waste paper basket that had a cover, then the total surface area would be the curved surface area plus the area of the bottom circle plus the area of the top cover. So we'd have to add in another pi r squared. So in total, it could either be 2 pi RL with no closed ends, pi r squared with one closed end, or 2 pi r squared if you have two closed ends. So this could actually work out to be 2 pi r L plus 2 pi r squared. Okay? So that's what that would look like if it was closed at both ends. Okay, so in this question, they ask you to calculate A. Write in, calculate A, part 1. The surface area in cm squared of the wedge. Right, this shape here is called a wedge. So they're asking you to find A, part 1, the surface area in cm squared of the wedge. Surface area in cm squared or centimeters squared of the wedge. That's the first part, right? Second part of part A is you have to find or calculate the volume in cm cube of the wedge. So A part 2 is calculate the volume in cm cube of the wedge. Okay, so those are the two things we have to do. Now in order to calculate the surface area of this wedge, we have to find the surface area of each of the faces of the wedge. Okay? Now what we are saying is we could calculate the area of the triangle EDC, right, which is the one right to the front, EDC, and we can, after we calculate the area of EDC, we will then know automatically the area of triangle ABF because they are the same triangles. So all we'll do is multiply the answer we get for ECD by 2. That'll take care of the front and the back triangles. Okay? Then we will do for the two slanting faces, if we consider it to be like a roof, each slanting side of the roof, and then we'll go to the bottom and do that. Okay? Now the area, one of the main areas of a triangle, right, you could write it here. The area we're looking for will be equal to, I'll use A to represent area of triangle, right, EDC, plus the area of triangle, and that triangle will be BFA. Okay, that'll be this one in the back there. Then the next thing we'll do to that, we'll add the area of the rectangle ABCE. Right, ABCE. What is that rectangle ABCE? ABCE is the left sloping side of that wedge, right? ABCE. Then we'll add to that the area of the rectangle BCDF. BCDF will be the left side sloping edge of that wedge, right? If you imagine it to be a roof, it'll be the side that it slopes down from the top down to the right that you can't see, right, in this drawing. It will be behind your view. So let's write that plus the area of the rectangle, right, that will be BCDF. And then the last thing we'll have to do is to find the area of the rectangle underneath. And that area will be AEDF, area AEDF. So we'd have to add to that the area of the rectangle AEDF, that's the underneath part. Okay, so that will be our task. Those are the things we'll have to find. What's the area of the triangle EDC? The area of the triangle EDC could be found by saying a half base by perpendicular height. Right? That's the area of the most basic equation we know for triangles. So it'll be a half base by perpendicular height. In this case, the base is 21 and the perpendicular height is 12. So it'll be a half by the base, which is 21, by the perpendicular height, which is 12. And we know that there are two of those. We know that there are two of those because EDC is the same area as BFA. They are the same triangle. So we'll have to multiply that answer by 2. Right? We'll have to multiply that answer by 2. If we work that out, whenever you work it out, you'll see what we get. The next thing is if we're looking at the area of ABCE. ABCE, that will be length by breadth. So you could use 76.5 multiplied by 20. Or 20 by 76.5, doesn't matter. So we use that here. This one will be 20 by 76.5. Okay? Then the next one will be area of BCDF. Right? BCDF. Again, if we observe here, this BC will be the same thing as AE. So that will be 76.5 centimeters as well on top. So length by breadth will be 76.5 for BC times the length CD. And CD has a length of 13 centimeters. So it will be 76.5 by 13 centimeters. Because this here is 13 centimeters long. Right, so it'll be 76.5 by 13 for area of BCDF. Or 13 by 76.5. So you write that in, 13 by 76.5. And then to get the last one, which is the base, the bottom, right? So get AEDF, which is the bottom part, that big bottom area there. You'd use length by breadth again, which would be AE by EB, which is 76.5 by 21. So we could write that in, 76.5 by 21. And what you'd find is if you work that out and you add each one in turn together, you would get a total area. Your total area, when you calculate it, would work out to be 4,383 centimeters squared. Okay, if you go through and you work out each one and you add them up together, you will get 4,383 centimeters squared for the total surface area. The next part of this question, which was A part 2, asked us to find the volume in cm cube of the wedge. Right, now volume of any prism, which this is the area of the regular cross section times the length perpendicular to it. Right? Now the area of this regular cross section here, what is the regular cross section? It will be the triangle. Right? The triangle ECD is the first viewing of the regular cross section, and if you go along the length CB, if you go in that direction, you will always find that same triangle no matter where you cut it along the length CB. So the regular cross section will be the cross section given by the area of the triangle ECD. Now we know the area of the triangle ECD from up here is a half by 21 by 12. So the area in the volume equation will be a half by 21 by 12 because that gives us the area of the triangle. So we write down in the volume equation a half by 21 by 12. Okay? that will give us the area of the regular cross section, which is the triangle ECD. And all we have to do now is multiply that by the length perpendicular to it, which will be the length CB, and that will be 76.5. So you multiply that now by 76.5. We're just following the equation. Volume of a prism is the area of the regular cross section by the length perpendicular to it. Once we do that calculation, we will get the answer 9,639 cm cube. 9,639 cm cube. So that will be the answer for A part 2. Okay, so you need to know some volume relationship. So you need to know that 1,000 liters is equal to 1 meter cube. Alright, you need to know that 1,000 milliliters is equal to 1 liter. 1,000 cm cube is also equal to 1 liter. 1,000 cc's is also equal to 1 liter. Right? And then some normal relationships for length. You're required to know that 1,000 meters is equal to 1 kilometer. In the same vein of conversion, 1,000 millimeters is equal to 1 meter. 100 centimeters is equal to 1 meter. 10 millimeters is equal to 1 centimeter. All these relationships you are required to know. You're supposed to know them offhand. From here, you should be able to see that 1 cm cube is equal to 1 cc, and that's also equal to 1 milliliter. Okay? Those things you're supposed to know by heart. They're not going to give you those conversions in the exam. You have to know that. In this question, you're writing the diagram above not drawn to scale. The diagram above not drawn to scale shows A, B, C, D, E, F. Shows A, B, C, D, E, F a vertical cross section of a container. A vertical cross section of a container with ED being the top edge. With ED being the top edge. Full stop. DC and EF are vertical edges. Starting over from the top, the diagram above, not drawn to scale, shows A, B, C, D, E, F, a vertical cross section of a container with ED being the top edge. Full stop. DC and EF are vertical edges. Full stop. BC and AF are arcs of a circle, BC and AF are arcs of a circle of radius 7 centimeters. Of radius 7 centimeters. BC and AF are arcs of a circle of radius 7 centimeters, and AB is parallel to ED. And AB is parallel to ED. Full stop. ED is equal to 30 centimeters. ED is equal to 30 centimeters. AB is equal to 16 centimeters. And EF equal to DC. And EF equal to DC equal to 9 centimeters. And EF equal to DC equal to 9 centimeters. First question is, part 1, taking pi to be equal to 22 over 7, taking pi to be 22 over 7, show that the area of A, B, C, D, E, F, show that the area of A, B, C, D, E, F is 459 cm squared. Is 459 cm squared. That's the first part. The second part, part 2, water is poured into the container. Water is poured into the container. Until the water level is 4 centimeters from the top. Until the water level is 4 centimeters from the top. Full stop. If the container is 40 centimeters long, if the container is 40 centimeters long, and has uniform cross section, comma, calculate to the nearest liter, the volume of water in the container. Calculate to the nearest liter the volume of water in the container. So, based on the information they give you, the drawing would have been initially like that. When you read on that ED was 30 centimeters, which is in there, AB is 16, so we have to put in AB as 16 centimeters. DC equal to 9 centimeters, that's in place. And then BC and AF are arcs of a circle of radius 7. So if AF and BC are arcs of a circle of radius 7, it means that here is 7, here is 7, here is 7, here is 7. Another very important thing is to label critical points. A critical point in this discussion will be here, which we call G, and here, which we will call H. Now notice they didn't give us that in their description. We made this up for ourselves, right? And as you do more and more of these, you'll realize that you have to do that. You have to label up your drawings accordingly. Okay, so let's look at the first part. They say taking pi as 22/7, show that the area of A, B, C, D, E, F is 459. So the first thing we'll do is we'll go about finding the areas of all the different shapes in here, right? The first and easiest shape, of course, will be a rectangle, all right? Any one of the two rectangles there. And then another shape will be that of the sectors FGA and CHB. Those two sectors are all important. So let us find the areas of the sectors. Let's get that out of the way first. So let's say we're going to find the area of sectors FGA, right? And also we will find the area of sector CHB. We'll do that one time. So FGA and CHB, we'll find those two areas. Now the area of any sector, the area of a sector will be a fraction of the total area of the circle it is associated with. Now the area of a circle is pi r squared, and this sector, this is 90 degrees here, this is 90 degrees here. That is the sector angle. That is what we will use to solve it. Now the angle gives us the fraction of the entire circle's area that sector will represent, theta over 360, where theta is this angle here. So if we had to put in the values that we have, we'd put 90 as the angle in the sector over 360 degrees, multiplied by pi, which we were told is 22/7, so we'll put that in, by r squared. R will be the radius, which should be 7 squared. Now remember, we are looking at two areas. So we'd have to multiply this answer by 2 when we work it out to get that area of the two of them that we're looking at. When you work that out, you actually get 77 cm squared to get the area. Okay? We did the area of sectors already, so if you forgot it, it's a revision. You can always go back and check it. Okay? The next one we will find is the area of the rectangle GHBA. GHBA, that's the area I'll be looking at now, which is this area in here. Okay, so we will calculate that, and that's easy. The area of GHBA is simply length by breadth, right? And we'll use the length by breadth of AB by GA, AB by GA, which will be 16/7. And that works out to be 16 multiplied by 7 is 112 cm squared. So the area of GHBA works out to be 112 cm squared. What else is left? We have to find the top rectangle now, which will be EDCF. Top rectangle, ECDEF or EFCD. So let's write that down. Area of EFCD. EFCD. Right? That'll be a length by breadth again, which will be ED by DC, which will be 30/9. 30 multiplied by 9. And that gives us a figure of 270 cm squared. Okay, so in that way we got all of the areas of the components in that section. So therefore, the area that they are looking for, which is that of A, B, C, D, E, F, will be the summation of those areas that we got. So we just add them up, the 77 plus the 112 plus the 270, and what we will get is 459 cm squared, and that is what we were asked to prove up here, 459 cm squared. So once you reach that part, all you do is put your double arrow like this, and that means that we have proven what they asked us to prove. Okay, when you add up the areas, this is what you will get. The next part is said water is poured into the container until the water level is 4 centimeters from the top. So if this is the top and it is 4 centimeters from the top, let's say it's lying at this point here, that's where the water level will be. It will be 4 centimeters away from the top here. So this will be 4 centimeters here, and therefore if this whole thing is 9, then the balance will be 5. 4 from 9 will give us 5. So this distance here will be 5 centimeters. Okay? They are asking us if water is poured into the container until the water level is 4 centimeters from the top, right? So you'll have water from here go all the way down. If the container is 40 centimeters long, which means if we go this direction here, that'll be 40 centimeters long. So that container, if it was going in that direction, right, that container will be 40 centimeters long if we are going in that direction, and has uniform cross section. Calculate to the nearest liter the volume of water in the container. Now to get volume, we have to use the equation area multiplied by length perpendicular to it. Now the area we'll be interested now in will be this area now. That will be the area we'll be interested in now to get the volume of water. Okay? And that area could be found by adding up the areas of the two arcs here and here, adding up the area of GHBA, which is this, and then adding in the new area, which is the area of from in this shape here. Now to make it easier, let's call this point here J, and let's call this point here I. Okay, so we can talk about it. So one way to get that area is to add up the two arcs, the area in between that, which will be GHBA, and add up this new area GICF to it. That's one way. Another way, some people might say, okay, so what about if we use the area that we got before and simply take away from it the area of EDIJ? Could do that as well, and you would get the same area that you're looking for. Okay, so it's all up to you which way you prefer. The way we did it was we found the area of JICF, right? So we wrote down area of JICF, and we got that to be 30 multiplied by 5, 30 on top, 5 here. So JICF would be 30 by 5, which worked out to be 150 cm squared. So all we'd have to do to get the area that we're looking at shaded in blue will be to add this 150 to the areas that we had calculated before. Okay? So therefore, area of JICBAF, which is the blue area there, JICBAF would be equal to, and we just add back all the areas that we need. Okay? So it'll be 150 plus 77 plus 112. 150 would be what we just got on top. 177 will be that for these two, and 112 will be for the one in the center. So we just add back up those areas, 150 plus 77 plus 112, and that would give us 339 cm squared. So the area that we are dealing with, where it is filled up to 4 centimeters from the top, will be 339 cm squared. That's the area that we have shaded in blue. Good? Why is that important? Because in order to get the volume that we are interested in, we need to take that area of cross section and multiply it by the length perpendicular to it, which was given to us as 40 cm. So the volume that they're interested in will be 339 multiplied by 40. And the answer there will be 13560 cm cube. Okay, that'll be the volume of the water. That'll be the volume of the water. That water will actually be going along this direction here. Okay? That would have been the volume of the water going in that direction. But what did they ask us? Let's go back and see what they asked us. They say if the container is 40 cm long and has uniform cross-section, calculate to the nearest liter the volume of water in the container. This is not in liters here, is it? So therefore, that's not the answer. We have to go to the conversions that I gave you before. You ask yourself, how many centimeter cube in 1 liter? And if you go back to your conversions, you'll see that there are 1,000 centimeter cube in 1 liter. So therefore, to express this in liters, right, you'll have to divide this here by 1,000. And that will give you the answer in liters. So it'll be 13.560 liters. However, have you answered the question? Did they just ask you the question in liters? The answer in liters? No, go back and see what they asked. Calculate to the nearest liter. That's not to the nearest liter yet. So to the nearest liter would be, to the nearest liter here would be 14, right? 13.560, you'd have to bring it to the nearest whole number. Because this number here is 5 or more, it rounds off to be 14 liters in all. Okay? So the answer finally is 14 liters. And that will be because it's to the nearest liter. Okay? To the nearest liter. Okay, so we'll close off with that today. The homework would be as shown on the right, but I'll put it up here for you. That'll be in certificate maths. Right, so that'll be certificate maths exercise 107, and the questions will be numbers 3, 4, 6, 7, 9, 12, and 21. Okay, you will not be able to do all as yet. You'll only be able to do some of them. Just do what you could do. Thanks.